Good day, everyone. Welcome to the fifth week of final term. Last meeting, we solved problems involving lenses and also we discussed how images are formed using geometric construction. This week, we'll discuss about first is Huygens Principle, second is interference, third is two-source interference of light, and lastly, problem solving involving Young's double-slit experiment. First, let's tackle about Huygens Principle. Geometric optics, the application of geometry and its laws to study the behavior of light, can be condensed into two laws. We have law of reflection and the Snell's law of refraction. Long before Maxwell's equation laid strong mathematical foundations for the derivation of these laws, a few scientists had already derived them. One of them was Christian Huygens. He applied the rule of geometry to light as transverse wave to derive the law of reflection and the law of refraction. His method was based on what is now called Huygens Principle, which states that every point on a wavefront is a source of wavelets that spread out in the forward direction at the same speed as the wave itself. The new wavefront is tangent to all the wavelets. According to Huygens Principle, you can freeze any wavefront at any time and think of each point as a source of little spherical waves called wavelets. These wavelets then travel expanding in bigger spheres. We can construct new wavefront from these wavelets by connecting points that are tangent to wavelets. This can be applied to plane waves and circular waves. Therefore, every point on the wavefront can be considered a source of spherical wave. Despite the simplicity of Huygens' model of wave propagation of light, it is very powerful guiding principle. We start by proving the law of reflection and Snell's law of refraction using Huygens Principle. First, let's prove law of reflection using Huygens Principle. To show the law of reflection using Huygens' wave propagation model of light, we start with a reflecting surface. Okay, so the rays of light are incident from the top left, and with that, we can draw the wavefront anywhere perpendicular to these rays. Because the light wave hit the surface at a slant, they do not all arrive at the same time. When the leftmost wave hits first, okay, so as you can see, we have incident ray, and if we have incident ray, we also have reflected rays. Okay, so going back, Huygens would start a wavelength at that point. Okay, so this wavelet gets bigger with time. When the middle wave hit the surface, a wavelet starts at that point and this wavelet gets bigger in time also. Okay, during this time, the leftmost wave is already bigger. Okay, as you can see in the illustration, the first wavelet is bigger than the second wavelet. Okay, so by the time the rightmost wave hit the surface, wavelets from the two other waves have reached the size indicated by the pink circles. Following the Huygens principle, we now construct the reflected wavefront from these wavelets. And the new wavefront is a straight line connecting points tangent to the two pink circles. So this is the wavefront of the reflected waves. Okay, now let's use Huygens principle in proving law of refraction. So we'll now attempt to apply the Huygens principle in order to arrive at the law of refraction. Okay, particularly Snell's law. As you can see, we have two mediums, medium 1 and medium 2. First, let's draw the interface between these two medium. Okay, so always remember that medium 2 is denser than medium 1. Okay, first we draw two incident waves as shown in the illustration, and when the wave on the left hits the interface, the one on the right is still traveling in medium 1. Okay, so we draw the wavefront through this point, and subsequently the left wave slows down as it goes through medium 2. Okay, since medium 2 is denser than medium 1, it is now traveling at a slower speed. Okay, when the right wave hit the interface, it also slows down. Okay, so we now draw a wavefront through this point to the left wave. Okay, but during the time between the two waves entering medium 2, wavefront bends because its two ends are covering different distance. Okay, so we construct the new wavefront from the tangent to the wavefront on the left and the one just emerging at the right. Okay, from this refracted wavefront, we can now have our wavelets. So, since the Huygens principle states that the new wavefront is tangent to all the wavelets. Okay, so the wavefront now, as you can see, the wavefront now are tangent to the wavelets. So this is where wavelets are formed. Okay, so with that, we can now draw our reflected rays. So the blue lines here are the wavefronts, and let's draw a straight broken line there, orange straight broken line, to indicate the normal line so that we can identify the angle of incidence and the angle of refraction. So in here, this is our angle of incidence. This is now our angle of refraction. Okay, next let's proceed. So next, we have interference. Okay, so what will happen when waves overlap? Okay, when two people sing together, the sound waves they make add up and the combined singing is louder than each person singing alone. Okay, so this is governed by the principle of superposition. So what is the principle of superposition all about? The principle of superposition states that when two or more waves are at the same place at the same time, the resultant disturbance is the sum of the disturbance from the individual waves. Okay, so like sound waves, light is a wave and also obeys the principle of superposition. Okay, when two light waves pass a point at the same time, their electric fields combine according to the principle of superposition in order to yield a combined electric field. So we have no way sensing changes in electric field because we are not superhuman, but we can sense the change in brightness of light. Okay, so now the square of electric field vector is directly proportional to the intensity of light, which in turn is related to brightness. So there are two kinds of interference. We have constructive interference and destructive interference. So first, let's tackle about constructive interference. So as you can see, we have a two light wave as the same frequency and wavelength as shown in the GIF presented. So the wave the two waves are in phase, which means that every instant each wave is at the same part of its cycle as the other. Okay, so they are crest to crest and trough to trough. Okay, so when they overlap, the result is constructive interference. Next. Okay, next is destructive interference. Okay, destructive interference class is the brightness of light diminishing. That's why we see shadow. Okay, so in destructive interference, the two waves are said to be out of phase by half a wavelength. Okay, so as you can see in the GIF presented, so while one wave is going to its crest, the other is going to its trough. Okay, the two waves cancel each other out everywhere. Okay, instead of adding the displacement along the y-axis, we subtract them. Okay, so as you can see, if we add these two waves here, okay, the sum will be a straight line since it cancels, the two wave cancels each other. Okay. Okay, since we already discussed about interference and the two kinds of interference, now let's proceed to the two-source interference of light. Okay, so in optics, coherence is often achieved by splitting the same beam into two, as Thomas Young did in his famous double-slit experiment, or by reflecting the light from two thinly spaced surfaces. Okay, the famous Young's double-slit experiment made history because it was critical in demonstrating that light behaves as a wave. Okay, so in double slit experiment, we need a source of monochromatic light such as laser. Okay, the two barrier between the light source and the screen are added. Okay, so the first barrier has one central slit and the second one has two narrow slit. Okay, these are separated by a small distance called d. Okay, so the screen is a distance L away from the two slits. So the distance between the two slits and the screen is called L. Okay, so we also define a horizontal axis shown as a dashed line that starts from a point halfway between the slits and goes to the center of the screen to a point labeled as O. Okay, from point O, we measure the distance y to an arbitrary point P. Okay, so the distance between O and P is our y. Okay, always remember that because we will use that in order to solve double slit experiment solving. Okay, as you can see in the photo, interference pattern has double slit from double slit experiment. So these are alternating light and dark bands starting from the central light band. Okay, so the central constructive interference there is called the central maximum and the other bright fringes are called maxima. Okay, the bright fringes there are the constructive interference and the destructive interference there are called minima. So using the double slit experiment, we'll now have this equation. So sine theta is equal to the change in path all over the distance between the two slits. Okay, so which give us an expression of the path difference. So we have constructive interference and destructive interference. Okay, so in constructive interference, we have d multiplied by sine theta is equal to m multiplied by the wavelength or lambda. And in destructive interference, we have d multiplied by sine theta is equal to m plus 1/2 multiplied by the wavelength. Okay, next, we have this equation. Okay, m multiplied by wavelength all over d is equal to y max all over L. Okay, so we equate this with the sine theta in the condition for constructive interference for Young's double slit experiment. Okay, so with that, we have now our formula in bright fringes. So y max is equal to m multiplied by wavelength multiplied by L divided by d. And our formula in dark fringe, y min is equal to m plus 1/2 multiplied by wavelength multiplied by L all over d. Okay, so next, let's solve problems involving Young's double slit experiment. So, let's start. First, let's have this example number 1. Violet light with a wavelength of 410 nanometer shines on two slits 4.0 millimeter apart and forms an interference pattern on a screen 7 meters away. Okay, so determine the spacing between this fourth and the fifth dark fringes. Okay, so let's start by finding all the given. First, let's identify all the given in the problem. So we have our wavelength 410 nanometer converted into meter, 410 times 10 raised to negative 9 meters. Our D is 0.4 millimeter, convert that again to meter, 0.4 times 10 raised to negative 3 meter. Our L is 7 meters, and our M is 3 and 4, okay? Why 3 and 4? Because the first dark fringe is formed when m is 0. Okay, so first let's identify the distance between the central bright fringe and the fifth dark fringe. Okay, so y fifth now is equal to m plus 1/2 multiplied by wavelength multiplied by L all over d. Okay, substitute all the given. 4 plus 1/2 multiply by 410 times 10 raised to negative 9 meters multiply by 7 meters all over 0.4 times 10 raised to negative 3 meter. Okay, so we'll have this answer 3.23 times 10 raised to negative 2 meters. Okay, next, let's identify the distance between the central bright fringe and the fourth dark fringe. Okay, so y fourth now, using the formula again, let's substitute the given. Y fourth is equal to 3 plus 1/2 multiplied by 410 times 10 raised to negative 9 meters multiplied by 7 meters all over 0.4 times 10 raised to negative 3 meters. Use your calculator and we'll yield up into this answer. 2.51 times 10 raised to negative 2 meters. Okay, since we already get the distance between the central bright fringe and the fourth and fifth dark fringe, okay, therefore the change in y now is equal to the y fifth minus y fourth. So y fifth is 3.23 times 10 raised to negative 2 meters minus 2.51 times 10 raised to negative 2 meters is equal to 7.175 times 10 raised to negative 3 meters in distance between fourth and 5 dark fringes. Light of wavelength 505 nanometer falls on a double slit forms an interference pattern on a screen 9 meters away. If the distance between the slit is 0.28 millimeter, find the distance between the sixth bright fringe from the center. Okay, so first let's identify the given. What are the given? Our wavelength is 505 nanometer. If we convert that into meter, that is 505 times 10 raised to negative 9 meters. And our D is 0.28 millimeter. Convert that into meter, we have 0.28 times 10 raised to negative 3. Our L is 9 meters and our M is 6. Since the problem is focused on bright fringes, so our formula now is Y max is equal to M multiplied by wavelength multiplied by L all over D. Okay, again, let's substitute all the given. We have 6 multiplied by 505 times 10 raised to negative 9 meters multiplied by 9 all over 0.28 times 10 raised to negative 3 meters. Okay, so the answer is 9.7 times 10 raised to negative 2 meters. Okay, therefore, the distance between the 6 bright band and the center is 9.7 times 10 raised to negative 2 meters. Okay, next and last example. A student projects a 2-point source light interference pattern onto a whiteboard located 5.25 meters away using a laser and a double slit apparatus. 8.56 centimeter is the distance between the central bright band and the fourth bright band. Okay, a distance of 0.145 millimeter separates the slit. Okay, so the question now is, what is the wavelength of the light measured to be? First, let's identify all the given in the problem. We have 8.56 times 10 raised to negative 2 meters. D is 1.45 times 10 raised to negative 4 meter. L is 5.25 meters and M is 4. Okay, so first let's derive the formula of wavelength using this formula. Y is equal to M multiplied by wavelength multiplied by L all over D. Okay, so using that, derive the formula. So we'll come up with this formula. Okay, wavelength now is equal to Y multiplied by D all over M multiplied by L. Okay, so substitute all the given. So we have wavelength is equal to 8.56 times 10 raised to negative 2 meters multiplied by 1.45 times 10 raised to negative 4 meter all over 4 multiplied by 5.25 meters. Okay, so everybody kindly bring out your calculator and let's solve. Okay, so we'll come up with this answer. 5.91 times 10 raised to negative 7 meters. Okay, so therefore, the distance between the fourth bright band is 5.91 times 10 raised to negative 7 meters. And before we end the lesson, let's reflect on this quotation written by Brené Brown. Okay, so the dark does not destroy the light, it defines it. It's our fear of the dark that casts our joy into the shadows. Okay, so Brené Brown wants us to understand that darkness in our lives is not always a bad thing. Sometimes it shatters us, but this is when we realize that we must face our darkness in order to see the light in every situation. Kumbaga, silver lining ba? Okay? We will never understand what the light is for unless we have experienced the dark. That's all. Thank you for listening and have a good day and God bless.